So for today, we are doing a little bit of a review for the test. We just have one last little section left, and there's nothing new to teach. It's just, here's a practice proof. So why don't we start with that? We're going to do a bunch of practice proofs. Got a whole bunch of strategies that you could employ. By now, I'm just going to read them off briefly for those at home that might not remember these strategies. One strategy is if you can factor it, you should. And as I look at this, I don't see anything that lends itself to factoring. So probably not factoring. Creatively replace a 1. Well, there's 1s all over the place, so that is a possibility. So you could leave that as a, maybe I'll creatively replace the 1, as in like with cosine squared plus sine squared or something like that. Option C, you could break up big powers like sine to the third. There aren't any big powers like sine to the third of theta. There's another option, change everything into sines and cosines. Well, I guess if we worked on the right-hand side, we could try that. Another option, common denominators. Ooh, I do have two fractions, and they don't have a common denominator, so maybe that's a good idea. Last strategy, conjugates. Conjugates are like if I have 1 plus tangent, I use 1 minus tangent. And actually, conjugates could also cause you to end up with a common denominator, which would be like 2 of these strategies at once. That might be a good idea. All right, I know most of you guys are already partway done with that. I'll pause while you try to finish this proof. Here we go. All right, so we're going to start by multiplying by 1 plus sine theta here and here, because that's the conjugate for this. And that should mean you get 1 minus sine squared when you multiply it out. First outside, inside, last. All right, and over here, I'm going to multiply this by 1 minus sine theta, and I have to do it on the top then also. And again, my denominator comes out to 1 squared, which is 1, minus sine squared. On the top, it's much more complicated, because on the top I have 1 plus sine theta, and this minus right here goons a lot of people, because they think, oh, it's just the opposite of the other one, so they're both going to cancel. Nope. It's minus 1 minus sine, which if I distribute it out means that's a negative 1, and a positive sine theta, which makes it sine theta and sine theta, which makes 2 sine theta. How many got 2 sine theta on the top? Okay, that's one of the most common mistake places. On the bottom, I could replace 1 minus sine squared with cosine squared. Then, I personally like to break up the cosine squared into cosine times cosine. So I'm going to do that. So cosine theta times cosine theta. That's the same as cosine squared, right? But why did I do that? Because now, right here in the middle of my problem, I have a sine over cosine. And what is sine over cosine? Tangent. So then, I have 2 tangent. And you might be saying, but isn't the tangent on the bottom? No. We have a sine over a cosine, and that makes tangent. You could say tangent over 1 if you wanted, and that shows you the tangent's on the top. This cosine is on the bottom, so therefore it's over cosine, and that's what I was asked to prove. If I go back to the top, 2 tangent theta over cosine is what we were supposed to get, and we got it. Were there any of those steps that you are having trouble understanding? All right, then here is another problem I would like you to try. Prove that the red left side can be changed into the right side. And don't do this. Oh, it's so frustrating. People think, oh, I can cancel these 2 cosecants and I can cancel these 2 cotangents. No, that does not work. I know it seems like that could work, but it doesn't. It's kind of like saying if I had 1 plus 5 over 7 plus 5, that I could cancel these 5s. You can't do that. That doesn't work. When it's over an addition, that won't work. But can you factor it? If you can factor it, you should. Okay. The top ones are both squared. So yes, that is cotangent squared. I'll clarify that. Better? Okay, I hope this one was easy because by now, that's the difference of squares. You should be able to just fire off cosecant squared minus cotangent squared would be cosecant minus cotangent, and cosecant plus cotangent, because it's a perfect square. And you take the square root of this and the square root of that, and with a minus and a plus. All right, and it's all over cosecant. I'm just recopying this bottom line here, minus cotangent. And that makes a perfect cancel. There we go. That's all there is to it. I hope that one felt easy. Yes? I hope so. Just factoring. Factor the top, cancel something. That's kind of a one-stepper. That would be like an R2 level type question. All right. As long as you know what to factor. There's really not too many things that you could have done instead of that. You could have changed it all into sines and cosines, but when your answer is supposed to be cosecant and cotangent, that doesn't seem like a good strategy. So, all right, let's try another one. That is in the middle of a problem. What could you pull out and do some replacements on? I mean, what part of this? Give me some options. There's actually like 10 things you could do with that part of the problem. Yes, sir. This whole thing could be cosine squared. I agree. Could pull it out, put in cosine squared. Option B. What else could you do with it? You could factor it. Does everybody see that that can factor? Into what and what? 1 plus sign and 1 minus sign. Okay, good. Give me something else. Yes. Yes. I could pull out the 1 and I could put in lots of things. Sine squared plus cosine squared is one of them. Or cotangent, or what's the one we just did? Cosecant squared minus cotangent squared is equal to 1 also. How do I know that? Because the 1 with the coat is cozy. I have memorized. You have a sheet. And then if I want to get 1 alone, all I got to do is subtract cotangent from both sides, and it ends up being cosecant minus cotangent. So I could pull that 1 out and creatively replace it. Lots of options. I could pull out the sine squared, couldn't I? And the sine squared itself could be 1 over what? Cosecant. Sine is a 1 over cosecant. It is squared, but these are called, I like to call them sister functions. They're actually called reciprocals. All right, so there's a whole bunch of options when you have like a 1 minus sine squared. So you really got to think through what makes the most sense in the problem that you're in. All right, here's another one. Try proving that this is true. Something completely different. Some haven't looked up yet, which means you're not really paying attention. If you have a new problem, please try this one. Okay, one of the strategies was break up the big powers. So sine to the 4th could be made into sine squared and another sine squared. In this one, I recognize, what is sine squared over cosine squared? Tangent squared. And I can just cancel these off, right? No, I would not allow that on the proof. I'd have to show each little separate step. So what I just showed was a step. I would need a separate line for that. Now I'm going to do a separate line where I let these two things cancel. Now I'm going to have sine squared over 1 minus cosine squared. And then, ooh, what's that? Okay, I just did something wrong. I apologize. I canceled the two things that were supposed to turn into tangent. My bad. Let me try again. These two turn into tangent squared. Okay, so then I have sine squared theta over 1 minus cosine squared times tangent squared. And that was this turning into tangent. Now, I know these have to cancel, but you can't just say, well, they must cancel, so I'll cancel them. You got to replace one with the other. I personally would replace this one with what? Sine squared. And that means then, of course, those two can cancel. And that'd be 1 times tangent squared. And the theta there. And that's just tangent squared theta equals, bring it down all the way from the top there, tangent squared theta. And that's a proof. Raise your hand if you can do that. All right. That's what the test is like. Now, I've got one more style of problem. And then I want to have you give this one a shot while I am playing something kind of fun, because it's going to take you a little while to answer this one. And I'm celebrating Pi Day a little bit early. So first, a quick Pi Day question. Would you agree that the Earth is round? If I took a cross section, it would be approximately a circle. Other than there's some mountains in there, and it's not perfectly round, by the way. The Earth actually is not perfectly circular, but for all intents and purposes, it's pretty much a circle if I took a cross section. Now, imagine I had a rope that went all the way around it. I don't know if you know this, but the diameter of the Earth would tell us the distance around the Earth. It's about 25,000 miles. I'm rounding, but it's about 25,000 miles around. So can you imagine in a world where we just ignore the little details, like some of the rope would be in water, some of the rope would have to go up and down a hill, etc., that I could have a rope that would go all the way around the Earth and then connect again. And I could make it like super tight, so it like all is just tightly around the Earth. Okay? Theoretical, but can you imagine a rope that could go all the way around? That would be called its what? It's a circumference, right? All right. Now, here's the question for you. If it was super tight all the way around the Earth, and then I cut the rope and I add 10 feet in, 10 feet of rope get added in, just 10 feet total. Remember, it was, how long was it in the first place? 25,000 miles. I'm going to add 10 feet. Do you get that that's almost like not adding anything? I mean, really, 10 feet compared to 25,000 miles, it's pretty much rounds to nothing. But then, imagine, could I grab my rope now that it's got this extra 10 feet in it? Could I grab it and lift it over my head? Well, it depends on how tall I am. Do you get, if I was like 4 feet tall, it's going to need to go up and down again, right? If I was like 4 feet tall, I could raise the rope over my head. But here's a much more ludicrous question. 12-minute warning there. What if I wanted to have a whole bunch of people all around the world raise it over their head? No way, right? I mean, all the way around the world? I only added 10 feet to it. So how much could you lift it up if I had some guy in China lifting at the same time as me? And add in another guy in Greece, and add another guy in, I don't know, Thailand, wherever. So across India, there's people all over the place lifting up this rope. Now, it gets smaller and smaller amounts that you can lift, right? Because if I'm trying to lift and the other guy's trying to lift, it's going to like be less rope for us to lift, right? So if you have an infinite number of people all the way around holding onto this rope and lifting it up, how high up could I lift it? Yes, sir. I'll tell you in a moment, but do you get, if I had an infinite number of people lifting on it, I can't lift it very high at all because I have an infinite number of people trying to lift it. All right, well, here's the math proof, and I think you guys are into proofs right now, so I think it'll be cool for you to see. So, would you agree that circumference equals circumference? I hope you're not going to argue with that. Okay, would you agree that circumference equals 2 pi r? Does that ring a bell? You ought to know that one for the ACT. All right. Do you agree then that I wanted to add 10 feet to my circumference? It was 25,000 miles around, and I'm going to add 10 feet. Do you agree I have done it right so far? I just added 10 to my circumference. Okay. Now I got to do something to the other side, though, right? Would you agree? Of course, I could add 10, but would you agree that it would be the same as the radius getting a little bigger on the Earth? Think about that. The radius from the Earth is going to be getting a little bit bigger, as in we're lifting it up, right? The radius of the Earth, this huge number of miles, is getting a little bit bigger. I'm going to put plus x. Now, I haven't cheated. Believe me, I haven't cheated. I'm just trying to show you the math on this, that the radius has gotten bigger, but I just don't know how much. And now it's 10 feet bigger of a diameter. Okay, so then to solve this, this is where the little magic happens. 2 pi r plus 2 pi x Do you get I have a 2 pi r here and I have a 2 pi r there? And I could subtract the 2 pi r's from both sides. And then, it isn't a divide, it's a subtract. And now I'm going to have 10 equals 2 pi x. Incredibly easy to solve. I'm going to divide both sides by 2, and I get 5 equals pi x. And I'm going to divide both sides by pi. And it's 5 divided by pi. Now, that comes out to 1.59 feet. Isn't it weird that I can lift it up 1.5 feet around the entire Earth? I can lift it up 1.5 feet just by adding 10 feet. 10 feet gives you enough slack to get 1.5 feet, more than 1.5 feet. And here's the thing that's really, really weird to me. Now put it the same exact experiment with the rope around the sun. Now I know the rope would burn up, but imagine a rope that couldn't burn up, okay? So it goes around the sun. And then you add 10 feet to it. Still goes up 1.5 feet. All the way around the sun, which is so big that 1,000,000 Earths could fit inside it. Why? Because I never even put in the radius. So the radius could have been anything. Doesn't matter how big your circle is. Now shrink it down, and it's the size of a basketball. And you have a rope around your basketball. And then you add 10 feet to the rope that goes around your basketball. And now you hold it out equal distance around the basketball. It's 1.5 feet again. Isn't that weird? Now let's go to the entire universe. You put a rope in a circle going around our entire universe, not just our solar system, not just our galaxy, the entire universe in a circle. And you add 10 feet to it, and you pull it out away from the universe. It goes out 1.5 feet. True. Hard for your brain to deal with, but true. The ones you could test that'd be fairly easy is put a little string around a basketball, then add 10 feet of string and pull it out from the basketball. Comes out to 1.59 feet. You'll know you're onto something. Then put it around something bigger than that and add 10 feet to it, and it'll go out 1.59 feet. Weird. Yes? Okay, now we're going to get into how do you put a rope around the universe. I know you can't really, but maybe I should have stuck to the solar system where you could, like, imagine a circle around that. So, okay. So, while you work on this problem right here, where did it go? Hold on a second. I didn't ever actually write it for you. It's on the board in the classroom, but I'm going to write it for the people at home. This one's going to take you a few minutes. You're going to draw me a few circles. Sine of alpha is equal to -1/2 in quadrant 3. Next, I'll write in a different color here. Tangent of beta is equal to -√2/2 in quadrant 4. That's two separate drawings. Now, figure out for me what's sine of alpha plus beta. I'll pause while you give that a shot. Okay, so let's answer this one. First of all, this is my triangle in the quadrant 3 that would have sides of, with this being alpha, opposite -1, hypotenuse 2, and then if that's 1 and 2, this looks like it should be √3 to me. Would you guys agree with that so far? Okay, good. Then over on the other side, what? Oh, did I have a negative missing? Oh, you're right. You might actually, it is the most common mistake in circle trig, and probably the most common mistake in all of this honors pre-calc is just forgetting negatives. Okay, back over to the other side. Tangent beta, so that's in quadrant 4. I'm going to just draw a quadrant 4 triangle, and tangent beta, TOA, opposite over adjacent, and then this side is beta, or this angle is beta. I don't know that third side right off the top of my head, but if I square this and I square that and I have a square root of those added, it would be 4 plus 2 would make 6. Would you guys agree on square root of 6 for that side? Excellent. Then, let's get sine of alpha plus beta. There's an app for that. You look it up on the form and it tells you what to do. Okay, so you look it up on the white sheet, and could you read for me, please, what sine of two things added is? Sine alpha times cosine beta plus cosine alpha sine beta. Did we find the right one? Do you guys agree that that's the right one for this job? Because it was sine with an add. There's only one place where there's a sign with an add. I think she's got it. Yes? Okay, good. Then I'm going to put in the actual answers for each of these. Now, here's where a lot of people start figuring out what the angle is and thinking, well, what do I do with the pi over 6 or whatever? We don't want that. We want sine of that angle. So sine of this is opposite of hypotenuse, which is negative a half. And couldn't I have just got that from right here? Sure, I could have. Cosine of beta, though, is nowhere up here. Beta's over here. So cosine of beta, I better go in that triangle and find cosine of that one. Cosine is adjacent over hypotenuse. So 2 over root 6. Plus cosine of alpha, back to this one, except this time I need cosine, which is adjacent over hypotenuse. So negative root 3. Glad you guys caught that negative mistake there. Negative root 3 over a cosine adjacent over hypotenuse is 2. And then the last one is sine of beta, which is in this triangle, and sine is opposite, negative root 2 over hypotenuse, root 6. Now, one of the things that's kind of cool on these is you always end up with a common denominator automatically. See how that's 2 root 6 and that's 2 root 6? And that has to do with the fact, would you agree that sine and cosine are both have hypotenuses on the bottom? And so these are hypotenuses, the hypotenusae. And therefore, if you always multiply the two hypotenuses from your two triangles, you'll always have a common denominator. So anyway, then this is negative 2 over 2 root 6 plus, I guess you could say negative times negative makes positive root 6 over 2 root 6. Now, I know you could cancel those root 6's right there, but you don't really want to because you want to use the common denominator thing. So since I have a common denominator of 2 root 6, let's leave it that way. And on the top, we can put negative 2 plus root 6. And there is your final answer. Now, other than the simplifying at the end, how many of you think you had it? All right. Are there any questions about, wait, why is it this way? Because I can answer those right now. Yes?
For the negative, or for the root 6. Right?
For the root 6, yes? How come that's not negative? Because it is a hypotenuse, and therefore it cannot, by definition, all the hypotenusae have always been, they're like a radius, right? They're always defined as positive. They have to be positive. Yes? Okay, you could have canceled those, but then you can't add your fractions together because they don't have a common denominator anymore. Oh, okay. Why can't I cancel those root 6's? Because one of them's being added. Yeah, you can't do that. Yep, that is. Yep. And I'm glad being aware of it is the first step, right? Being aware you make this mistake. Stop doing that. All right. So are there any other questions about this one? That was a tough one. That was a hard R3, I would agree. Yes. What? When I got, okay, you guys are laughing too. Don't do that. He's trying to talk. When you got a square root of 3, what? At the beginning, we got a square root of 3. Okay. How did I get that? Okay. If you want to do this the other way, you would go square root of this side squared and that side squared, and they got to be subtracted. You just added, didn't you? Okay, that happens all the time. All right. Any other things you want to ask? Because you guys are showing that you are not afraid to ask, which I really appreciate because it helps you and it helps me to help you so that you hopefully can understand what happened. All right, so now I think I've covered everything that I wanted to get you ready for this test. So that's all I have for the video for today.